afternoon, or good evening, whenever you're watching this video. On the last video, which I will link down below in the description, we built a machine learning model with the iris dataset. And I mentioned a bit about overfitting. So on today's video, we'll talk about overfitting precisely, like what it is, why it happens, and how to prevent it. So stay tuned for it. Okay, so we are now in the Jupyter Notebook. This is on the Kaggle platform. And this is a notebook that I had already prepared in order to discuss today overfitting. So here we have like a little bit of the agenda of today, like what you will learn, what is overfitting, why it happens, and more important, how we can prevent it. Okay, so in the first part, we will explore like the challenge that is overfitting, and we will try to understand what it is. Okay, so overfitting basically is when the model learns too well the data from training. Okay, so maybe it gets not only the data required, but also it's getting some noise that in this case is irrelevant. So before we start with the actual exercise, I would like to tell like a kind of real life example of what overfitting is. Okay, so in this case, overfitting, I'll bring like a real life example. Let's say you have a dog. Okay, you have a dog and its name is Rusty. And Rusty is just a puppy, maybe less than a year born. So you want to teach some tricks on Rusty, okay? Like for example, sitting. Okay, so you tell Rusty to sit, you instruct it a few times, you push it a little bit, and then you give him maybe a cookie, okay? And after maybe a few days or a few weeks of training, Rusty actually comes to obey you. He starts listening to you, he starts to pay attention to your instruction, and it actually sits. You're very happy at it. Then you want to go to the park to show off with your friends, and then you bring a Rusty, and right when you're like with your other friends around, you want to show them the trick, then you tell Rusty to sit, and he doesn't care. He's not paying attention. He's not doing it. He's not performing the trick that you wanted, and it's a little bit embarrassing for you. So go back to your house, to your apartment, maybe, and then you start training again. Rusty, feeling a little bit maybe disappointed because he's not behaving the way you expected, and then you realize that he's actually obeying you. Okay, um, maybe you train it a few times more, and then go back to the park, and maybe this time just by yourself you want to do the trick, and you realize he's not obeying you again. Okay, this could be because Rusty learned to sit inside the house. Okay, so maybe he's catching like, okay, the instructions sit but inside the apartment. Okay, which is irrelevant, right? The location should be irrelevant for the dog. Or let's say that maybe you train it always in the evening, like after you came from work, and he realizes that he's only going to do this instruction like in the evening, and maybe you took it to the park in the noon, so he's catching like the wrong instruction, like the he's catching some noise that is irrelevant for him to learn. Okay, so what you have to do actually is to train Rusty in different places at different times, so he doesn't catch this like this specific moment of day or this specific place. Okay, and that's a little bit like what happens in overfitting. In overfitting is that the model, the algorithm learns so well the data that it's been trained on that it's like it's adapting to every nuance that the data has. But then the thing is that when you're going to real life, when you're taking it to the park or to some other apartments like Rusty, when you are training with real life data that it hasn't seen, like places in this case where Rusty hasn't been, it's not gonna end that well. Okay, the model is gonna have problem with this data because it's already adapted well, so well adapted to the initial training data that it's not going to fit that well on on the data, on the test data. Okay, so let's follow now the instructions on the notebook. Okay, so first of all, we're going to declare a few imports here. Of course, we're going to use a matplotlib. We're going to do a little bit of plotting here. But also, one main thing is that we're going to load the data set, the iris data set. We're going to be working with the same data set that we used before. I like it because it's very small data. It's easier to understand, doesn't have those that many features, so it's very good for getting started in machine learning. We'll also use a decision tree classifier, and the first thing we're going to do is we're going to build this initial decision tree, and you will see that it is overfitted. So we'll learn why it's overfitted, how you can tell that it's overfitted. Okay, and plot tree, which will allows basically what I just mentioned to see why the tree is overfitted and how we can detect that behavior. Of course, we're using train test split because we're going to hold some data that we're going to like hide from the model. It's not gonna see it, but after the model is actually created. And of course, accuracy score because we want to measure what's the accuracy of the model. Okay, so first of all, we're going to load the data. Oh, first of all, we're going to import, and then we're going to load the data. And remember, always do some short exploration, a little bit. Okay, in this case, we're going just to refresh our memory with what is the data inside the iris dataset. Remember, there are several different plants. These are their features, the features of the flower, like the petal length and the petal width, and other measure from the sepal also. And the target is very important because the target is where we want to point. Okay, it's our goal to go there to the target. There are three targets, three classes. One is setosa, the other is versicolor, and the third is virginica. So this zero means that these first five are all setosa. And actually, if you remember, the first 50 are setosa, the other 50 are versicolor, and the last 50 are virginica. Okay, so we're going to split the data. Okay, and we're going to do a 25% in this case. So we're going to keep, I don't want to do some math in public, so I'm just going to use here Python as a calculator. So we're going to keep 25% the 150 rows. This will be in this case 38. 38 rows will be kept um, for the will be kept apart from the model. The model is not going to see these 38 rows. And here we're going to do the splitting. And after that, we are going to build the model based on this data. So what we just did here, remember, train test split, it's going to divide the data set into some data from training, uh, training and testing, and then some target will be split also into target training and target testing. So the model is going to be built with data trading and target training. Okay, so we'll only have what's this 75%? We'll have 112 rows. 112 rows to build the model, okay, from the 150. From those um, from those 112 rows, we're going to build a model, okay. Another thing is the random state. You saw it here and here. And random state, it's it's how the behavior of the model or the function, it would be deterministic, okay. So in this case, we are to assign this number, this basically random number, but this number decides how we will influence how the train and test splitting will occur, okay. And what we do here is that we want to guarantee some reproducibility, okay. So I want the data to be split in an exact way that I can go back and split it once and over. All right. And this random state is for the machine learning model, and it's how it will be built. Okay. So I intentionally use like different numbers here and here, which is to tell you that they are not related. You don't have to use like the same number. You just, no matter what number you use, just use the same number in that function. Okay, so use the same number always here in the splitting, and then use the same number that you decide for building the machine learning model. All right. Um, so what we're going to do here is that we're going to uh, build some accuracy from the model to evaluate the accuracy of the model. So in this case, the model in training has 100% accuracy, and on testing it has 97%. Okay, so what's happening here is that we are evaluating how accurate the model is with the training data. So we give, once the machine learning model is built, we give it the data from uh, the data that was used initially in the training. So we use it as input, okay, and build the model. But now what we are going to do is that use the data and tell the model, based on what you see here, try to predict what would be, okay? And remember that we already have the answers. Let's say for this, and we're going to do, let's say, for example, for these 10 rows, I already have these 10 answers, okay? So I'm going to send these 10 rows, okay? And then tell the model, well, not this exact 10 rows, you'll see why. Uh, hold on. So we'll use 10 rows similar to this. And what we're going to do is that we're going to make make the model predict based on this input what the model think would be the output. So as we saw this in the video before, so maybe you want to go back and check that one if you don't understand this that well. So here, for example, target training, um, you'll see, and this is what I mentioned before, like we're not going to see the exact first 10 rows because it's randomly splitting them. Okay, so when I say here on data training, um, show me the first 10, these 10 are not necessarily their first 10 rows. Okay, so these are row 40, row 23, row 100, and so on. Okay, so this is uh, the training, the target training. Okay, so this is like the goal. Okay, so I have to predict 0, 0, 1, 1. This is the real data. And then I have here like the the prediction, the target prediction, what the model thinks. So this is like the correct answers, and now let's see what the model thinks. target, I'm using target train. Let's use data train. Okay. So as you see, it's very similar, I guess. 0, 0, 1, 1, 2, 0, 0, 1, 2, 1. It's very similar. It's identical to this. So the training data, it's behaving really well. Okay. But you'll see that that's actually a problem in a few moments. And then we compare the accuracy. We could do the same for test. So target test and data test. Okay, so the thing here, this target test and data test, the thing is that this is data that the model never saw before. Okay, it was data that, as it wasn't used for training, the model has no idea about its existence and how it's conformed. Okay, so this data in testing, the target is 0, 2, 2, 1, 0, 1, 2, 0, 1, 0. So in this 10, basically, it's a 100% match. But as you can see, it's actually a 97% when you evaluate the whole target, the whole 25% of the data. But to understand well why, like how can you can tell it's overfitting, first you see that it's working better with training than with unseen data. Okay, so this is a very like a bad indicator. It's behaving too well, too well. It should actually be a little bit less. In real life, what you actually desire is in training, it doesn't perform that well, but what really matters is in test accuracy. So here, for example, it's working a little bit worse in unseen data than on data that it has already seen. And then you can see on the decision tree. So we're going to plot the decision tree. We're going to use matplotlib and of course plot tree. All right. And as what you can see here is that this is the decision tree that actually built the machine learning model inside. And what you see is that there are like many options. Okay, so a decision tree classifier, it works like based on some decision on some range, you can go left or right in the tree. Okay, so for example, um, when the petal length is less than 2.5 centimeters, then I'll have 112 samples. Okay, so then it will go to the left. Okay, and then to the left, we'll have 38 samples. And from those 38, it divides into this. Sorry, this isn't that one actually. It just ends here with 38. But then on the right, you'll see when it's the petal width, it's less than 175 with 1.75. And then I have 35 from one class and 39 from the other class. Okay, so as you can see, for example, for Setosa, it was very easy. Okay, so for Setosa is whatever is the petal length less than 2.5 centimeters, it's going to end up here. So and so on. You can see the decision tree here, like all the conditions. But what you can see, like on the leaves, like a leaf is like the final node. On the leaf are some of them have very few options. Like for example, this one, this class Virginica here only has 2 for Virginica, and this leaf here has 1. for versicolor. And then this Virginica, this node here also has one for Virginica, and so on. Here there's two for versicolor, and maybe three here for Virginica, and so on. So as you see, the model it's for some leaves is very specific. Okay, some the model is like breaking up breaking up the tree in very specific features for very specific rows of the data set for very specific features. Okay, so for example, yeah, as I said, like this node here with Gini equals 0.0 has only one sample. Here, this leaf has only one sample. This has two. This has three. So as you see, many of the leaves, uh, most of the leaves actually have like two, um, two or maybe less rows, two or one rows. So that indicates like a model that is overfitting. As I said, remember in the past example about Rusty, Rusty was learning about some exact patterns, like the exact time of the day, or maybe the exact place where he was being trained at, and that didn't actually matter that much. So it was like really specializing for some things that it detected, but shouldn't be actually included in the model. Okay, so what we can do here is that we can reduce the complexity of the model. Okay, and we do this, for example, we want to prune the tree. And what this means is that the tree won't be that depth here. Here, for example, it has like uh, 1, 2, 3, 4, 5, or even more, five levels, okay, levels of depth. And we don't want that. We don't want the model to be that much depth in this case because there isn't that much data. We only have 150 rows. And if we continue like building a larger and larger tree, it will be really, really specific for every, almost for every single case. And we don't want that. So what we're going to do is we're going to like prune the tree and limit its growth. Okay, so in this case, what we want to do is that we're going to do to reduce it the the depth of the model to only three levels. Okay, and we will continue using the random state 1, 2, 3, and we'll use this criterion entropy, which it doesn't matter right now, but it will create a better model for us. Okay, so in this case, the accuracy of the training it decreased a little bit to 97, but also you can see that the testing it sustains. It keeps being 97%, so we didn't lose um, that much of the accuracy of the model with data that it hasn't seen during training, right? So now if we plot the tree, we are going to realize something. Okay, so now you see the three levels, 0, 1, 2, and 3. You see there are only three levels here. And it's very interesting because as you see here, you don't have that many leaves now, but also they have more data inside the leaves. Okay, remember on the last one there were leaves with only two. Uh, this one is two. This one's two. This one has one. This one has only one. Okay, so as we did this, we decreased the complexity of the model. So it's not going to be like a really large tree, but it's gonna, in general, to behave more accurate than our previous model, which was really really specific, really like creating some specific leaves for very specific cases. This one generalizes really well. As you see, the here the leaf with less data has three. Okay, that didn't. I think that didn't happen The last one. Okay, here we had one with three, only one leaf, but we had one, two, well, one, two, three, four, five, six, seven, 8 leaves. Okay, while here uh, we only have one, two, three, four, five, and that's I think enough for a case of a data set that is not that large. That it's only, as you remember, it only has 150 rows. Okay, so what we did here in order to understand is that we basically reduce the complexity of the model, and it's very important to understand it. But there are other ways to reduce overfitting and to also understand why it happens. Some of the other techniques that you could learn are, for example, cross validation, where you split the data set into multiple training and validation sets. And then what you do is compare them to see, it's like creating different distributions of the model, different cases, and then realizing and comparing how well it behaved when you split the data in a different way. Okay, that's a very interesting one. Another could be feature selection, where you maybe identify or remove irrelevant data for tests for the training. As I said with Rusty, for example, Rusty shouldn't be interested in location. So maybe if Rusty was a machine learning model, I would remove the location column in this case, or for example, the time column. So no matter what time it is, the dog should obey the word sit. Okay. So I hope this has been really um, interesting for you, this content. I'm really happy to make this. I hope you have grasped the details about overfitting, what I'm trying to transmit here, the main idea. So thanks for watching until the end, and I hope you can subscribe to this channel, like these videos, and I hope we can keep posting these videos. So see you in another video coming up. Bye bye.